We are here to do more C. That wasn't my idea, it was Anna Grace's. Blame her if you don't like it. Okay, but first we review. All right, so Monday we went over stack-based arrays, the stack, and pointers. So let's start with stack-based arrays. What can you tell me about them? Anyone?
Sorry.
It was really cute.
Huh?
It was really cute. You guys did it at the same time.
Okay, anyways. I do remember from the other day that the stack works from the top down.
That is true.
It's like first in, last out for memory.
Okay, sick. What is important about the size of stack-based arrays?
It builds down and it can
No,
rise to the heap.
So not the stack, but stack-based arrays, right? So the arrays that we made were stack-based arrays. And the important thing about the size of those arrays is that they have to be declared. Okay? Because they are static sizes. They cannot change for stack-based arrays. So if I make a char array of 128 bytes, it's only 128 bytes. That 128 bytes isn't going to go anywhere or be anything else except for a part of that array. Okay? Cool? What is a what would be an array of chars? A string. Sick. Okay, so strings are just arrays of chars, or a char array, and normally we just like put random numbers in there to make it as big as possible. So we talked about the stack, right? We said it grows from the top to the bottom. That's cool. Yeah, it's the so if it's from, where does it start from? What kind of addresses does the stack start from? High addresses. Sick. And then goes to low addresses. Okay. And then finally pointers. What do pointers do?
They hold an address pointing to some other variable.
Sick. They hold the address of some other, well, I wouldn't say variable, of some data, right? That's on the stack. Yeah.
Is that the one where we do the ands and the asterisks?
Yeah, ands are pointers, right? So who remembers what the and sign is for? Or the ampersand, as it's normally called?
It's address of. So if you do ampersand and then some variable, it will give you the address of that variable.
Yep. It's so address of. It's also commonly referred to as dereferencing as well. So then what would the asterisk be? Reference, which gives what?
It accesses whatever is at that space.
Sick.
At that address.
Sick. Perfect. You guys are now experts on stack-based arrays. Okay, so what are we doing today? Heap-based memory, okay? So we talked about how there's a stack and it goes from high addresses to low addresses. The heap goes from low addresses to high addresses until eventually they meet in the middle and they get married and live a happy life. Heap-based memory is dynamic. So what that means is we, as programmers, must allocate the space ourselves, and we can dynamically allocate that space. Okay, so like the stack space, when you write your program, the program's like, okay, you get this much stack space. You don't get more of the stack than that, and that's it. Okay. For the heap, what you can do is say I have an array of size 2, right? I can then, while in that program, while during runtime, I can expand that array size to 4 using the heap, okay? And the heap's like, that's cool because like I had this space made for you anyways, because it gives you like extra space to do heap-based arrays or heap-based memory allocation. Whereas the stack, all you get is what you said you were gonna want, right? But for heap-based, it's you can get more based off of the needs of the program. Okay, does that make sense? All right. It has a special calling sequence, so there are function calls needed to allocate space and to free that allocated space, and so you use those function calls to then get back that space. And what each of the, well, not free, but what all the other ones return are pointers to a heap address that has the data that it's at. Okay, so this is why pointers are important, because the functions that we're about to get into, which are called malloc, calic, and realloc, only return back a pointer to you, and that pointer is just the address of the heap location where your data is going to be stored.
Would that be like the bottom of the heap, or where in the heap that the data is stored?
It's where in the heap the data is stored. And the cool thing about the heap is it doesn't necessarily go in order. Okay, and that's because you can take up this much space and then not use and not free that memory, and then keep taking up space, and then you would free this portion later, and then all of a sudden that portion's free. So now when the next time you allocate space, it'll take up that space that you just freed. So it doesn't have to go in order. The heap has some extra stuff. Basically, there's like set bits and stuff that tell you when it's the end of a sequence and stuff like that. It gets complicated. No need to really get into that. That's actually what the other room is doing today, is trying to break that. Okay, so the first thing that we use to actually allocate space on the heap is called malloc. Obviously, that means allocate. Okay, so because we're going to allocate space, we as the programmer must make this space on the computer, or to reserve this space on the computer for us to actually have. Okay, so the way you do it is you have a pointer, and that pointer has already been declared before this, so it's an int star pointer. Okay, and then when you're doing malloc, malloc returns a void star. Okay, who remembers what void is?
It's like it's a function that doesn't return anything.
So then what would the void type be?
No.
Not null, but no type. Okay, so now, but it's the void type. Okay, so if we return a void star, that means we can cast that void star to anything. So basically what happens is malloc returns a void star pointer because it doesn't know the type of what you gave it. It doesn't care because it's going to work agnostically of whatever type you're going to cast it to. And so basically what that int star in parentheses does is cast it to an int star. So it says, hey, the type of this thing is an int star. I want this to be an int star. Okay, so that's casting. You know, like how in Python you can just like write int and then parentheses in the thing that you want to turn into an int, or like stir and turn it into a string. It's the same thing, except for the parentheses go around the type that you want it to go to, and then it's the thing afterwards. Don't know why it's that way, but it is.
So
Yes.
if it's part of if it's like an int casting, I understand that, but why is it int star instead of just like int? And then is that
Because what does malloc return?
Okay, so it returns a void type, which is a star.
But it returns a void star.
Void star, okay.
Because it's gonna return a pointer to an address, a pointer to a spot on the heap. Okay. Because a pointer is just an address, right?
Mhm.
So if it were to return int, that would just return like a number, right? But it's returning an int. It's returning a void star. So anything that's void star is automatically a pointer. So it's just returning a void type pointer, because technically you can just have a pointer that doesn't like it. What the type of the pointer means is it's specifying what kind of data should be at that address and what it should be interpreted as. Okay. So that's all types really mean, is like, hey, the data that's stored in this address or in this variable should be interpreted this way. Okay. So technically you can have a void star that points to just some address, and that address has information that follows it, but you're going to have to tell the computer later what that should be interpreted as. Does that
So
make
it's
sense?
casting into an int star.
Yes.
Got it.
Okay. And then inside, what you have to put inside is the size of the array that you want, or the size of the thing that you want. So that's the n. Okay, so n is the size of our array. So say n was 5, we put 5 there. Okay, and then you also have to multiply that size by the size of the data type that you're storing. Okay, and that's because the way malloc works is it only it's reserving this by bytes. So really what's going inside of malloc is the total bytes of space that should be stored. Okay, so it's like, hey, like if you wanted to just store a char, right, I could just put 1 inside of malloc and then it'd be cool because I'm just gonna do 1 byte. Okay, but if I want an array of chars, then I would just need to put in, right? But because other types have so like an int is 4 bytes long. If it's 4 bytes long, then I need 4 bytes per number, right? So for each slot on my array, I need 4 extra bytes. I need those 4 bytes. If it were a char array, I only need 1 byte, so I can just put in the size of the char array.
With it being dynamic,
Mhm.
so say you try and put, if it's the n of 1, right, it's an array with only one thing in there, but then you try and throw a double into it, would it lose half of the data, or would it dynamically increase itself?
No, it doesn't dynamically increase itself. You have to when I say dynamic, it's still you who has to dynamically increase things. You would lose 7 bytes of data. Are we cool on how malloc works? We're gonna look at Calic and then free. We're gonna look at Calic, realloc, and then free, and then I'm gonna show how you actually use them in code. We're cool so far? Okay. So the next one is Calic. And as this meme here states, Calic is kind of better sometimes. All right. So malloc is good if you want to do things fast because it's just going to allocate memory, but it's not going to do anything with that memory, okay? Calic is cool because when it allocates that space, it's going to zero out everything in that space. So like say I wanted to make an array, I can make an array, and then Calic is just going to zero that array out so that every index in that array already starts with the value of 0. But if I were to malloc that array, then whatever was previously stored in that heap address is going to be in there, and it could be literally anything. So sometimes we want malloc because we want it to go fast. Sometimes we want it to be Calic because you want your arrays to be zeroed out for certain things. Okay, so the way Calic works is literally the same way malloc works, except for you don't have to cast it to something. So you can just say int star arr equals Calic. All right, and then the first argument. So this one takes 2 arguments rather than just 1 argument of the total bytes. This one takes the size of the thing that you want to allocate, and then the size of its data type as the second argument. Okay, so this is an array that's 10 long, and it has the size of int, so it's a int array. The size of function is just a function that returns the size of the data type that you pass in. Questions on Calic? Okay. The next one is realloc. Okay, so this is what we're talking about the dynamic reallocate. Oh, the dynamic, like it being dynamic. We can just reallocate space. Okay, so we can say, hey, I have this array already. Okay, that's the first argument. So you give it an array that you've already allocated space for as the first argument. And you're like, hey, I have this array. I now want more space for this array. So then you say, for the second argument, the same arguments that would go into malloc, which is just how big the array is supposed to be times the size of the data type that you're storing in the array. Does that make sense? So I like in the meme, it's like you have freed us, and it's like I wouldn't say freed, more like under new management, because it's like, hey, I'm gonna take this space, but it's like really what's stored at that pointer is now a part of a bigger thing. Yes.
So it's taking that like int array of like 5 in this example, and only it's like deleting the last 2 integers in it.
Mm-hmm.
So like using the example in the meme.
Mm-hmm.
So initially you have this PTR, it's an int array size 5, and then you reallocate it. Does that just delete the last 2 ints in the array?
Yes.
Okay. And does it actually zero them out, or does it leave them there?
It just leaves them there.
Okay.
But that space is now free for somebody else to use.
Okay.
Because for some reason the programmer has realized that they don't need those extra 2 bytes, and those extra 2 bytes could go to something else. And I know it seems like kind of weird to like worry about those extra 2 bytes, but for like programs where you're really trying to save memory, so let's say like you're writing a rootkit or you're writing some type of malware where you need to be really memory efficient so that you don't get caught by like antivirus scanner or something like that, that you're not using up a bunch of memory, so you're not slowing down the computers like a crypto miner or something like that. You want to be as memory efficient as possible so that you don't get caught as easily. Yes.
And what if you resize it to something larger and it runs into something else in the heap?
It won't.
Okay.
Unless it does, then you're out of heap space, which is like crazy that you're out of heap space, because like it'll keep giving you heap space.
Okay.
So until you're out of heaps, basically if you run out of heap space, you run out of RAM and swap, which is like you're using a whole lot of stuff, or there's a lot that's going on in that computer.
Well, I guess what I'm asking is, it seems like
it doesn't
in your
just
heap, you keep
expand it
adding
in space.
to the top, right?
Yeah, but it doesn't just expand it in that spot. It'll copy, if it needs more space, it'll like copy that beginning portion over into a larger spot.
Okay.
There's a lot that the heap can do. It could also split up the data into separate sections, and it knows to jump to that next section where it's at. Like the heap does a lot of cool stuff that basically there's pointers inside the heap at the end of each heap location that points to the next location that should be the next part of that array, or where it should go next.
Okay.
Cool. Any more questions?
I have a question.
Yes.
With the stack, you said once like a function has been called and it's returned its value, if I'm thinking about it correct, that portion of the stack goes away.
That is correct.
Is it the same type of thing? Does that also happen with the heap after a function call is over?
No. Which is crazy, right? Because it's like, what? But that's because each function gets its own stack portion, right? So like it gets its own little stack, basically. The heap is just for the whole program. And we'll see how to get rid of that. Yeah, with free. So, free, right? Literally it's just free, and then the name of the pointer to the address. Okay. So you have to free it to get to like let that space come back to the to memory. If you don't free it, you have memory leaks. And so there's information that like basically like you're taking up space that's unnecessarily being taken up. But additionally, with those frees, there's like things called double frees and other things like that that are called heap exploitations, and you can get some really cool but very complicated attacks with the heap exploitation stuff. So a lot of people will end up using heap space in their programs rather than stack space to avoid for security concerns, but then they don't realize that they're actually putting a lot of other security concerns inside their program if they're not freeing things correctly, or they're not freeing the right amounts, or they're doing things incorrectly. Any questions on how free works? And we'll see how like all this actually works in a second. Yeah. Okay. So let's look at an actual example. Okay, so we'll start this out the standard way. Okay. And then we get int main. All right. So we'll just make a simple array. And we'll do for size of int. Okay. And for int I. So what we'll do first is I'll show you how Calic zeroes out this array. So for int I equals 0, comma I less than 4, I plus plus. And then we'll put some new stuff in it instead after that, and then print those out. Well, actually, we'll do that while we're printing this. We'll do that. So, basically all we're doing is we're going to calic out some space for our array, okay? We're going to print the current values in the array to show that it's zeroed out. Then what we're doing is we're assigning now those initial spots just the value of I, which should then go 0, 1, 2, 3. And then we'll print that out. And then after I show that this works and how that works, we'll then realloc after this again, and we'll realloc to double S size. And then we'll fill in that portion after that. And then I'll show you why freeing is important as well after that. So we're not going to free anything up right now. Well, and we are going to because I'm afraid. But we'll free something up right now. So really free is just like that. And normally all your frees are written at the end of your program. BCC, yes. I forgot to put a new line right here. Okay, right? So when we calic the array, zeroed it out, right? As I had promised. And then basically everything else with the array is the same way that a normal array is, right? 0, 1, 2, 3, all that regular stuff. Nothing else has changed other than the fact that this space is now allocated on the heap, which means we can now reallocate it so we can expand the size of our array, and that we have to free this memory at the end of it. Okay. So if we wanted to realloc, do something like this. And then we'll do the original array, and then we'll let's make it 8 times size of int. Okay, which now means that these spots on the array 6 and 7 all need values, right? So we'll make the values and we'll make them 4, 5, 6, and 7. So for the realloc, we're just saying that, hey, instead of our previous array being that, we're just going to reallocate it to another array that's of a bigger size. Okay. Did something wrong. Good. What did I do?
Doesn't matter that your second form doesn't have its first track.
That would matter. Yes, that is exactly what would be a matter. I hope. Yes. Good catch. Okay, so right, it really just allocated more space so that we could double the size of our array. Pretty sick. I know, having looked at Python already, right, it's like kind of less cool, but like when I learned C for the first time, I hadn't learned any other language. I was like, whoa, this is crazy. Like now my arrays aren't whatever I define them as. A side note from cyber stuff, this allows you to do what's called amortization in C, which is basically doubling the size of your array every time you need more space. So, long story short, it's more computationally effective to just double your array every time you need more space rather than increasing it by the amount that you need, because every time you double an array, it has to copy over everything that's in that space. And so then, like, there's a curve, runtime stuff. Kind of cool if you like that kind of stuff. If not, then it's super boring and you hate me. Anyways. Okay. Let's not free this array. Okay. Nothing happened, right? Nothing crazy. Let's use this tool called Valgrind now. Okay. So what Valgrind does is it shows us if we have memory leaks within our program. And then it also helps you find seg faults and other things like that. So if you're trying to do C++ or C debugging, super helpful. I will clear this screen because I can see people trying to long neck. All right. Or I will first install Valgrind. I love when it says, like, please ask your administrator, and it's like, but I am the administrator, so that's kind of awkward. May I speak to your manager? Well, I am the manager. So, yeah. Okay. Boom. All right. So, right here, it says heap summary. In use at exit 32 bytes in one block. Total heap usage 3 Alex, 2 freeze. Right. It says we definitely lost 32 bytes in one block. How big of an array do we have?
We had like 8, I think.
Right. How many bytes are in each one of those spots? So we lost 4 times 8 worth of bytes. We lost 32 bytes worth of heap space. Basically, that means since we didn't free those 32 bytes, that RAM is lost until the computer restarts. So
I thought you put free at the end though.
I just removed the free.
Okay.
So if I put the free back, if I put this free back here, I didn't lose none, right? So this is important, very important. If you're writing a C program that is large, or you're writing a C program on your VM and you haven't allocated it a lot of space, i.e. your name is Cade Heckle and you're writing an IC210 project, you crash your VM because you forgot to put a bunch of frees and you ran your project multiple times. This actually happened to Cade. You could ask him about it. He crashed his VM because he forgot to put some frees in. I also crashed my VM because I also forgot to put frees in. The frees are important because if not, you'll have memory leaks, and then you you lose RAM until your computer starts it back over and the RAM space gets cleared. It's the only way to get it back. It's also important because that lost space can be used for malicious attacks that are they're very complicated to understand and pretty advanced. So we're not gonna talk about how it is, but like know that that's a thing for the future that we can that's pretty cool and pretty dynamic that we can do. Okay. There's something else I want to talk about. Give me a second. I don't remember. Oh well. Okay. Questions, comments? Yes.
Yeah, so in terms of like memory leaks, what is the danger of those? Would it ever become like accessible information?
Yes. Yeah. So a good attacker can leverage memory leaks in a program to basically write their own things to the heap, or leverage the things that were written to the heap to get access, to get like read access, or like to run things that shouldn't be ran. Yes.
This might sound really dumb, but can you like say for I in and then like start at address 0 and then just increment by 1 and then just say like free the address and then just clear everything in your heap? Or does that not work?
I don't know.
Okay.
Is the answer. Doesn't sound real because the heap doesn't start at address 1.
Okay.
Right? The heap starts at like OX4 something, right? Other questions?
Can you repeat that question? It was about using another program to free seat space?
Yeah.
That was? Okay.
Or you could just press the power button. Much easier. Other questions? Okay. How do we feel on C overall? Pretty good. Like you've done it for 2 weeks? Are you Cyber Major?
I was.
You were.
A new minted comp sci.
Oh, that's beautiful. That's a beautiful thing. Okay. Because I know the Cyber Majors are learning C right now in their class, and like I've been told that I've taught them more than they have learned in their class. So
I've learned more in C than I have in C++. I feel poor.
yeah, I'm sure. Okay. All right. I'm gonna stop sharing because that's gonna be the presentation for today. Okay. 1 second, please. While I end this.